Hello everyone, and welcome to the RobotDynamics exercises. My name is Jan. I'm a PhD student at the Robotics Systems Lab, and together with a few colleagues of mine, we'll be organizing the exercises of this semester. Due to the special circumstances, this is also new for us, so we're doing this first time virtually. So excuse the occasional glitches. We'll try our best to make it a successful first run. The exercises will be structured in a similar way every time. I will begin with a short recap of the theory and basically explain or go through the relevant parts of the lecture and the theoretical background that should allow you to solve the exercise. This will happen in a video format together with a recorded whiteboard or my writing, which would otherwise be the board. And we'll see how that goes. Afterwards, we'll have a video session for question answers where you can get help, either because you have questions about the lecture material in general, or you're stuck with specific questions. And we encourage you to use that to get live support from one of us. That could also either be in form of a plenum where we discuss general things that are unclear and we recap some of the theory, or also in breakout rooms where we might look specifically at your shared screen and help you debug a problem that you have with the exercise. What's also very important, and I would encourage you to use that, is our, how's it called? Our Piazza forum, where you can ask questions and see questions of other students, potentially anonymous if you prefer not to see your name there, and help each other answer the questions there. So we will have access, of course, to that and confirm student answers so you're sure it's right. We also provide occasional answers for yourself, but the idea is that you can ask many questions, other people also see your questions, and if you do know the answer to a question, also post an answer to them. With that, I think we're set. So let's get right into the first exercise. The first RobotDynamics exercise is concerned with homogeneous transforms and coordinate systems. That will be, for some of you, a repetition because you've taken dynamics classes before. For others, it might be new. So we will go through it step by step and show you all the necessary components that allow you to solve the exercise. So in robotics, what's a very common problem is that you have a point that you call the base of your robot, and you would like to know where your end effector of the robot has to reach. So you need a way to describe the relation of those 2 points, your robot's base, which is maybe fixed to a table, and the end of your robotic arm that you need to go somewhere. So let's just call those points here A and B. And let's say A is our robot base and B is the point that we want to reach. So we need a way to mathematically describe how to get from A to B and what is the displacement between those points. So how this is done here is we use vectors, and we call the position vector that takes you from A to B R, A, B. So the subscript will tell you there will be 2 letters, tell you from where starting point to where end point the vector is going, and the little r means it's a position vector. This is the convention that we will adopt across the lecture. Now, just this RAB vector by itself is just, you can imagine it as a physical object. It's such an arrow. What allows you to actually describe it in a mathematical vector as a form of 3 numbers, 3 tuples, is a coordinate system. So the coordinate system, let me draw this top of here, will have axis X, Y, and Z. And the projection or the representation of the vector RAB in a coordinate system A. This is how we write it. We take a left subscript to denote the coordinate system that we represent it in. This now will be a tuple, usually in 3D, of 3 numbers that allows that you can write down and also implement in the computer. So this is what we call the representation in frame A. It's important to be clear on the distinction between the pure vector RAB, which is as a physical object but doesn't have a concrete description yet, and the precise representation in one maybe arbitrary coordinate system. Here we abuse the notation slightly because we call the point of origin A the same letter as the coordinate system, which we call also A. And this is quite common because often you have a base of your robot, which is defined by a center and an orientation. So that gives you the point and the orientation of the axis. So sometimes it might happen that we want to represent a vector in a different coordinate frame than we are provided. And what you need to do that is coordinate transforms. So imagine you want to represent the vector RAB in a different coordinate system. Let's call it C. So that means we have a slightly shifted coordinate system. Let me change colors for this. Which, for example, is rotated a little bit around the x-axis, which we call coordinate system C. And now, so this is C, the representation will be a different set of tuples than the original one, despite it being the exactly same physical vector, still pointing from point A to point B. And how to transform this is, as you've seen in the lecture, I hope, is a coordinate transformation, also called rotation matrix here, going from frame A to frame C. How to read this is that you have to read it from right to left. And to remember this, it's easy to see when we write the whole formula, because those two neighboring indices have to match. So coordinate rotation matrix from A to C takes a vector that is represented in A frame transforms into a vector that is represented in C frame. Okay, let's clean up the clutter here. The way how to find this rotation matrix, capital C, let me use capital letters here, depends on how your coordinate system is actually rotated. Here we have a rotation around the x-axis. So how this would look like is we have a 3x3 matrix with a 1 on the x-axis, cosine on the diagonal, and sine on the off diagonal. To decide where the minus on the sine goes, just think about how would a unit vector in the y or z can be projected. So in this case, the minus goes here. So, okay, so having said that, what's important, and in distinction to what we will cover afterwards, what we do here is a change in representation only. Meaning the physical vector has not changed at all. Rather, we have only changed how it is represented in a different coordinate system. That's why often this is also called just a passive rotation. And this is also why we call it C, or you call the matrix C instead of capital R for rotation matrix, because those are sometimes used for active rotations. All right, moving on. Sometimes, and actually quite frequently, we don't have just 2 points, A and B, but rather we have more points that we want to, whose transforms we want to chain along each other. Why this is necessary is because often our robot has multiple links, and going directly from the base of the robot to the end of the end effector, the tip of the robot, might be too complicated, and we can build it up much easier stage by stage. So let's imagine our robot has two links, one going from A to B and then one from B to P. At the end, we are, of course, as before, interested in the transform from A to P, but it might be easier, as you will see in the exercises, to calculate the transform first from A to B and then from B to P, because those vectors correspond directly to your link lengths. So it's easy to define or find tuple representations for them in their respective links. Now, as you will know from your math classes, the vector RAP can be represented as the sum of RAB plus RBP. If you look at the subscripts, that also makes sense because the neighboring ones match up. So we go just a little detour, instead of directly AP, we go via B. Now, this is a sum that works with general vectors. So still here, we haven't assigned a representation to them. Importantly, if you do this calculation either by hand or in a mathematical program like MATLAB, as we will see there, you have to represent those vectors in frames. And you can only do this addition operation if you're in the same frame. So meaning here, when we have a frame X, Y, Z that we want to that we can represent the vectors in, the sum here has to be in the exactly same frame. All of them have to be in the same frame, such that this plus is really a normal vector addition. Now, for the first part, this is usually easily doable because your original link is aligned with the base frame. So for example, you know, the first link just is 20 centimeters in X direction. But the second part might be difficult because the vector BP is usually much easier being expressed in B frame rather than A frame, because the B frame, let me draw it in green here, X, Y, Z, the vector BP is fixed in the B frame, so it's easier to find a coordinate representation there. So what we can do is write this equation as the first term from A to B in A plus, and now the second part, we turn it with the rules that we have learned in the previous slide into a rotation matrix plus our times our position vector R of B, R from B to P in B frame, such that the overall calculation is precisely the same, but it will be much easier to now express the vector BP in B frame. You will see why this is in the exercise. Great. So one very convenient tool to ease these kind of computations is the matrix called homogeneous transform. And what the homogeneous transform does for you is it transforms directly from a vector BP into AP from B into A frame. How we can write this is, when we summarize the above, is we write it in this form. So we have a homogeneous vector, which is the original vector plus another component, 1 below. And you can see, if you write the equation above in matrix form, we can write this as CAB R ABA 0, 1. This is a 4 by 4 matrix. RBP in B1. So this matrix, we call it TAB, is the homogeneous transformation between A and B. And what it does it takes the vector that points from your point B to P in B frame to the vector that points directly from A to P in A frame. So here, contrary to what we did on the previous slide, where we said it's just a change in representation, here we indeed have a change in representation and origin. So important, change representation and origin changed. So the left and right hand side of the equation do not describe anymore the same vector, rather they describe how to get from the respective origin points to point B, P. Great. So those are the two key transformations and matrices that you will use in this exercise. So rotation matrices on one hand and transformation or homogeneous transformation matrices on the other side. And the last part that we need to cover here is how to transform and concatenate those two operations. So let's go to the last slide of today. Let's first look at inverses. How to inverse, sorry about this. How to invert such a rotation matrix or homogeneous transform. So with rotation matrix, it's pretty easy. Rotation matrices are orthogonal matrices. So the transpose is actually the inverse. And what's also important to notice is that the rotation matrix CAB is the inverse of the rotation matrix CBA. And by the rule to the left, this is CBA transposed. So to invert the rotation matrix, you merely have to transpose it. And it also means it was before going from A to B, it is now going from B to A, just the reverse. So that's easy. Be careful with homogeneous transformations. It's not quite as simple. So this still holds. So if you go from A to B and take the inverse of it, it's like going from B to A suddenly. And by definition, this is CBA RBA B01, just by reversing A and B. But now, if we plug in the definitions of all those terms, you'll see that the inverse is slightly more complicated. So this is actually CAB transpose from above. And now CBA expressed in the terms that appear in TAB is actually RAB in A rotated into B. And then we need to take the negative of it because we want to go from B to A instead of A to B. And here, of course, 0, 1 stays. So when you also have to implement an inverse of a homogeneous transformation matrix, don't just do MATLAB.inverse because it will spend unnecessary computational effort to do that, because you know there's some structure in there, and for most parts it is just a transpose and a slight reorganization of terms. All right, so this helps you if you know the transform in one direction but not the other, so you know how to revert them. And final part is composition, so how to chain multiple of those transforms together. And this is as easy as it gets. So the rotation matrix from A to B, if you have an intermediate frame somewhere in between, would be CA to, let's say, frame P times C of P to B. So composition is multiplication for rotation matrices, but of course make sure that the two frames that face each other match. So you have to, if you think from right to left, it would be rotating from B to P and then from P to A. Okay, and for homogeneous transformation matrices, it's precisely the same, which makes them so convenient for implementation. So we have TAP times TPB, and you can simply plug this into MATLAB and potentially or easily find the transform from a very remote point, step by step, going back to your base through this rule. This is it. I think those are all the rules that enable you to solve the exercise. I will see you in the interactive session.